Hello, Laia. Hello, Jupen. I'm Javier G. Fernandez from the Singapore University of Technology and Design, and I'm going to be telling you a little bit about the work that we do in the Thermal Lab regarding the approach, our approach to sustainability through biomaterials and through bioinspired manufacturing. Let me pull up the presentation. Okay, so you should be seeing the presentation now. So as you can see from the title of this talk, we are going to cover a very broad and complex issue, and I mean with an emphasis on our work to solve it. But with this broad scope, it's impossible to address all the multiple aspects and branches in detail. So what I have done is through this presentation, I have put the article where you can go to get more information about that specific topic or that specific aspect. And all the articles are also in our website, the website of our lab. And if you even have more doubts and you have more questions that you want to ask, just write me an email and I will try to answer as best as good as I can, basically. So let's start. Plastic, that is going to be a kind of a common thread in this presentation, was invented in the 1930s, and soon after the invention of plastic, and without any governmental incentive, without any external pressure, only because the technological possibilities that the material opened, the whole world moved from an economy based on long-lasting items to what the magazine Life described in the 1950s as the throwaway living, and that's that article that you can see on the screen. So that article perfectly reflects the perspective of the new plastic age, or at least what the people was expecting from me, right? If you read those columns, basically the article explains how amazing is going to be the life based on single-use items. It specifically gives the sample of a dinner where you put your plastic tablecloth, your plastic plates, your plastic cutlery, and when you are done, you just wrap everything up and then throw them away and you put it in the bin, right? You don't need to do dishes, you don't need to do laundry, right? Everything is just disposed. And if you're watching this and you didn't time travel from the 1950s, you really know what are the consequences of that. And there is something in your head that is saying that was wrong, right? But it's not that in the 50s the people was bad, right? But at that point in our history, there was a lack of information. The first reports on the impact of plastic in the environment starts to arrive in the maybe early 60s. I think that the first one was a study of the incorporation of plastic into the nest of seabirds. At that point, they were quite anecdotal, but at some point, all those results stopped to be anecdotal to become impossible to avoid. They were everywhere, and there was something that an idea that started to be more and more obvious. That is the idea that the economic paradigm of a planet of infinite resources and infinite space for waste, it was a lie. It was obviously not fitting reality. The problem is when we realized about that, it was too late. Or still being too late. So because we could regulate some applications of plastic, right, and we can put restrictions, but we cannot stop it because our economy is revolving around the cheap manufacturing that the plastic brought to the table, right? If it wasn't because basically our economy will be really different to what it is these days. And the issue is that is you cannot unlink these two things, right? There is not only environmental issue related to plastic. There is also economics issue these days, because the most expensive municipality all around the world, right, is waste management. And what is even worse is like this, there is no indication that this growth of plastic and waste production is going to stop its acceleration, not even stop it at all. It's just stop going faster and faster, right? And we know for sure that the people is getting more aware about the problem of waste in developed countries, but we also know for sure that the production of plastic and the production of waste is not going to peak this century. Right now, it's like all the countries where I live in Southeast Asia are in extremely rapid growth of waste production, and is what is predicted is like all this kind of like growth is going to move into Africa by the 2050s, 2070, when they are in the same stage of development or developing that Southeast Asia is right now. Also, there is another complexity. So we are becoming more urbanized and we are becoming more developed, right? So our waste is becoming also more complex. All the items that we use are made of different materials, are made of different colors, from parts that are smaller and smaller. So what it means is like countries that historically had the waste management under control are seeing now how the cost to keep up is becoming unaffordable, and this is something that doesn't have like any is not going to end, right? So let me go to the specific case of packaging. I'm going to choose packaging because it's really easy to understand for everybody, right? But the kind of thoughts that are problems that we are going to be talking about, they are in general for every product. It's not packaging, is just a really good example of how our economy, manufacturing, and materials, they are like part of like a single story, and you cannot change one without changing the others. So packaging is actually like one of the main percentage of the waste all around, right? In developed countries, it's around 30%. Worldwide, when you include like countries in development, I think that the percentage rockets to around 50%. So, and from all those, like all that waste, like around like 20 to 30% is plastic packaging specifically. And you might think, okay, like solution is easy. We remove packaging and that's it. So we remove like half of our waste from the equation, and we are safe, right? So obviously we cannot do that, right? So because packaging is not a luxury, is something that we need, right? And of course we can find some examples of absurdly overdimensionate and wasteful packaging that they are like the only purpose is branding or marketing, right? But that's not the issue in general, right? Like the packaging that we have is the packaging that we need for a globalized economy. We have an economy that is based on mass manufacturing and supply chains that cover the whole world, and that require a protective and carrier function of the packaging, right? So we cannot eliminate packaging, right, or the wasteful packaging, because it's literally central to our economy. We can improve it, that's for sure, and we can make it less wasteful. And that is actually the approach these days, right? Like there are some examples there on the slide. So we can go for like removing material. We can like keep track of the energy that we use, or like even like find other sources of energy that are cleaner. We can actually like make packaging so it can be reused several times or have like different uses. We can actually design packaging or products in a way that they can be disassembled. What I say at the beginning, that is really hard to sort waste these days, because the complexity of like all these interlinked between materials and small pieces, and we can facilitate the use of materials that are that they can be recycling. But the problem is that still, while improving the packaging is something that we need and we really need it now, it won't be enough in the long run, and that is something that we know for sure, right? So we are continuously reading studies reporting like how enormous is the magnitude of the problem of plastic waste, right? But all of them, they can wrap up in in a study that it was published like maybe a couple of months ago, and it was the cover of the magazine Science, right? It was an international study that evaluated all the possible scenarios for reducing plastic pollution, right? It basically include like all the policies. And depending on how broad or how deep was the implementation of those policies, where we will end in X number of years. And the conclusion was equally strong and demoralizing, because even assuming the immediate worldwide adoption of all the strongest measures taken to reduce plastic waste all around the world, right? Even in that completely hypothetical scenario that we are not even close, and it's not going to happen, still enormous quantities of plastic will still accumulate in the environment. So the conclusion is that the only way to eliminate plastic and packaging and product pollution is to get rid, at least partially, of an economy that requires that kind of packaging and that kind of products. And if we change the economy, right, like packaging will also change, because packaging at the end is a product too, right? So, and this is very important to remark, that there is always like a back and forth relation between economy, products, and materials. And again, I want to repeat, don't get me wrong, improving the design and the materials for current packaging is dramatically important and is something necessary. And we are going to address in this talk our work in that direction. But what is also important to remark, and I want you to keep in mind, that is that this approach alone is not enough. Because the problem is not the material or the product itself. The problem is a society with an economy and a behavior more around those materials and that they were basically created in the 1930s. So, and changing that is difficult, but it's not impossible, right? As I start this talk, we have seen several times through the history of humanity the reshape of the global economy based on the developments and control of certain materials. I put the example of plastic, but stone, bronze, iron are also examples of materials that they suddenly change completely, like the society and the economy, right? And this is a key aspect, because what it means is that while there is a lot we can do now, to fully get rid of our waste problem, we don't need to substitute plastic with a material of similar characteristics and displace the problem somewhere else. What we need are materials that are significantly different to plastic. And those materials need to present a technological and economical advantage. So everybody is going to, or is going to be adopted for technological and economical reasons and not for ecological reasons, because we know at this point that that is not, doesn't have enough power to actually drive a society change. And we are failing to basically ask the people to change on its own just based on ecological reasons. So the good news is that we are surrounded by those materials. We have materials that are significantly different to plastic, and they work in coordination with nature, right? So take, for example, the strength of the spider silk and the toughness of nacre, like the impact resistance of mammalian bolts, the combination of lightweight and strength of balsa wood. These are examples of materials with extraordinary properties and engineering relevance. And in many cases, they surpass any synthetic counterpart. And the good thing is that they are perfectly integrated in the ecological cycles of Earth. But what is even more impressive is the extreme conditions in what those materials are made. Nature cannot extract limited resources from Africa and transport it across the world to purify them and then transport them to use them, right? Forget about energy sources like melting metals, melting plastic, reaching hundreds of degrees is not a possibility for nature, not even close, right? Nature, what it does is that it works with the most abundant components. Most of them, they are actually mechanically irrelevant, right? But they are available in every corner of the world in large amounts. So, and it works with them with almost no energy. And even though it achieves some of the most extraordinary materials in the world. And the secret of this is what we call the hierarchical design. Nature works by basically assembling components at different levels of organization, that they are like interlinked one with each other, right? Like look, for example, the picture on the screen, right? So that's the structure of the Afterpod cuticle. So you start with the chitin molecule, that is the small chain at the corner, at the bottom corner, and then take all these chains of chitin, and then they are aggregated into bundles, and then you take these bundles and then you aggregate them in a kind of a braid, and then you take all these braids and then you aggregate them in layers, and then you stack the layers and you stack them in kind of like a plywood structure, and then you go all the way up to the final shape of the animal, right? So all the way up from the molecule to the shape of the animal, they are building a perfect coordination of structures across, like in general, like 6 to 9 levels of organization, right? And we humans are really good, are very good fabricating at those individual levels. These days, we can mass produce at the nanometric level. We can do buildings, we can do roads, we can do other samples of civil engineering that are at the hundreds of meters scale. But what we cannot do is to fabricate simultaneously at all of them. We can't fabricate buildings where we have full control at the nanoscale and all the levels in between. And that's important because that is where nature shines, fabricating in a coordinated way with control at multiple levels. So with this idea, right, 8 years ago, we formulate a hypothesis that later becomes central in my research. So the hypothesis was like biological materials and the way they aggregate are two sides of the same coin. And they also evolve in parallel. Therefore, if we want to incorporate structural biological materials, right, or biomaterials in engineering application, it's not enough to have the ingredient, but we need to also aggregate those ingredients in the same way that they have evolved to be used in nature, right? So it's a mix between the chemistry and the design, right? And to demonstrate this, we replicate the insect skin, exactly the one that you have on the screen, right? So this insect skin, the cuticle, is the hard shell that covers the whole animal, from the stiff and strong wings to the flexible joints, right? This exoskeleton and the cuticle of the arthropods in general is a fascinating piece of engineering, right? It is secreted by the epidermis, and following that hierarchical structure that I showed you before, is built by a combination of layers of a polysaccharide called chitin, which is also on the walls of fungi and on the organic matrix of sea cells and crustaceans, and a protein called fibrin, which is the structural component of silk, and I'm pretty sure that Laia has already talked about it, right? So we extract fibrin from silk and chitin from shrimp cells, and we made a material that we call shrilk. So shrilk is a replica of the insect cuticle that not only reproduces design, but also does that using the same composition. And shrilk had an unexpectedly strong and light characteristics. But on top of that, it was fully biocompatible, I mean, in terms of medical application, and transparent. And and the most interesting part of it, right, was how those properties were achieved. Because when we took like these two components, when we took like the fibrin and the chitin, right, and we just like simply mixed them together, what we got was a material that was what we would expect, a material that is stronger than the weakest component that we use, and is weaker than the strongest one. So basically, it's in between like the two components that we are using. If instead of mixing them, we organize them in the same structure that they organize in the insect skin, what we get is a material that is twice stronger than the strongest components that we have used. And that was the key, and that's the most important part, like beyond all the properties of the material, that was the key result. Because what we demonstrate is that by linking the biological design of the cuticle with its composition, we can artificially replicate the synergy giving rise to the outstanding mechanical properties of the insect cuticle, right? We can actually harvest the properties of biological composites. We can start using biomaterials in the same way that nature uses it. And for doing that, for being able to demonstrate this replication of the natural synergy, we didn't modify the biological molecules. So what it means is, like, in the eyes of nature, the plastic sheet that you are seeing on the screen that I'm holding there is insect skin. So it's not something that looks like insect skin. It's not something that it was inspired by insect skin. It's indeed insect skin. So it's metabolized and it's integrated into the ecology of Earth in the same way that the insect is integrated and metabolized in the in nature. So instead of remaining there and remaining like as a promising lab material for the future, we went beyond that, and we went into study the mechanics of the process and the important factors giving rise to the synergy, to that synergy between these two materials. And with that information, we rethought the whole fabrication process to enable the manufacturing of common items, right? So we started fabricating objects. We work on functional coatings. We develop a chemical route to recycle the materials, assuming that there is a recovery system in place, right? That there is, like, as we will see later, that's actually like a very bad assumption. But I mean, as a first approach, it's okay. Let's assume that there is a recovery system, and then we are going to recycle the material, right? We even include color in the components, in the products that we did. We include like a step based on drug delivery, so we can basically like remove the color before starting a potential recycling process. So what we basically were doing was to avoid the sorting color that I was mentioning at the beginning of the presentation, that is needed in plastic and is actually bottlenecking the whole process, right? We measure the degradation of the material in soil and the impact of that degradation in plant growth. We literally, like, or we basically move this material that start as a hypothesis from the scientific question to answer industrial questions. And a bunch of companies, very big multinationals, came to us interested in the material. And we became kind of like famous for this achievement, right? Because we have been called the future of manufacturing, the solution that can change the world, right? And the thing is, even if that sounds a little bit hyperbolic, right? It wasn't completely grown. Like listen what we already like demonstrate at that point. What we demonstrate is that potentially any structural biomolecule can be applied into engineering if we can correlate it with its native design. And think about all the new possibilities of the organic waste and the amount of mechanically relevant components that you even have in your organic waste in your household, right? And those conversations with the companies were extremely eye-opening. But it was also obvious at some point that we were talking a different language, right? Like the industry was very interested on a substitute material that can be introduced in the existing process with minimal changes, right? And get at the other end of the process of the production line, exactly the same product that you had at the beginning, right? But now like fully sustainable. But the problem is that those manufacturing technologies were based on the principles of synthetic polymers. So they use pressure, they use temperature. We fabricate everything at room temperature. For us, our language is the language of the biomaterial. So we were talking about pH, we were talking about water content, we were talking about the conditions for biology. So we found ourselves in a crossroad, and we need to choose. We could modify the material to show the thermoplastic properties of the current, or like they are required for the current technology, and then like moving away from the natural principles of the native molecule, right? So basically, like what we can do is like produce another bioplastic, right? So it can be easily introduced in the existing manufacturing process at the cost of ecological integration, because obviously every modification that you do of the molecule that is making it different to the natural molecules, the harder it is for nature to actually understand and incorporate in its own ecological cycles. So what is the other option? So we can develop from scratch a technology that works under the principles of biomaterials or biological materials. So in other words, we had to decide to what I call in my second slide, right? So we are going to decide if we are going for the incremental change or we are going for the long-term solution. And we went for the second. So we took our Bioinspired manufacturing approach. All the lessons we learned from the fabrication of Shrilk and all the lessons from the industrial translation, right? And we start over. But this time, we not only focus on the material, but we also focus on the tools, on the sustainability, and in the industrial application, right? So we base our research on cellulose and chitin. So they are like the first and second most abundant organic molecules on Earth, because they are produced and degrade in every ecosystem in extremely large amounts. So, and on top of that, they don't compete with food production because they don't have like nutritional values, right? So that gives us a chance to potentially scale up any technology based on these materials, right? And globalize the technology. And when I say abundant, right, I want to remark this, I mean abundant and natural levels of abundance, not human or technological levels of abundance. So the bioproduction of chitin, for example, that is, and again, this is the second most abundant, it's not even like close to cellulose. So every single year is equivalent to more than 300 years of worldwide plastic production at the current rate, right? So imagine what we are seeing, right? If we were able to capture all the chitin produced, not the system, produced in 1 year on Earth, we'll have enough to support all the manufacturing of plastic for 300 years, right? So those are more like natural levels of abundance, right? So, but there is also something very interesting about these two polymers, right? And we are going to get into the biology here, right? Chitin and cellulose are really abundant and broadly distributed across many natural kingdoms, right? But they are very rarely appear together in the same organism. And what is even more interesting is that they usually appear in organisms that they are in competition, right? Like they feed from each other, or they like have like this kind of competitive relationship. But they coexist in a really, in a very weird and a small group of microorganisms called Omnisets. And these are like kind of like a water molds that are classified as a fungus-like organism. And that's a really polite way for a biologist to say, I don't know where I can put you, right? Because you look like a fungi, but you produce cellulose. So you cannot be a fungi, right? But you are not a bacteria or an algae because you produce chitin, right? Since you are kind of like in the middle, you look like a fungi, but you are not a fungi. So I officially going to call you like fungus-like organism, right? And the good thing is like, even if these omnisets are so rare, right? Their outer world is extremely well studied and characterized. And that's important for us because that's exactly what we are aiming for. We want to get to understand how nature uses these two components together, right? And it's very well studied because these omnisets are a very aggressive pathogen for fish and plants, right? So actually, this small guy, this Omnisets, right? So where the cause of the Great Famine in Ireland when they actually wipe out a full season of potato crops across the whole country in the 19th century, right? So, and if you want to destroy a pathogen, the first target is always the defensive wall, right? So we took all the information on the composition of the wall of Omnisets and specifically the relation between cellulose and chitin, and we demonstrate that if these two components are aggregate following the biological design of the Omniset wall, right, we can make strong materials without chemical modifications, without using adhesive, right? And we call these materials the fungal-like materials. So these fungal-like materials, or flams, as we call them, so they are not only light and strong, but also they are perfectly integrated in the ecology of Earth without the need of a recovery. They are also extremely cheap, so they are about like $1.6 per kilogram. They are now as cheap as a commodity plastic, and they are 20 times cheaper than the cheapest plastic filament like PLA or ABS, right, used for 3D printing. Being made of the two most abundant components on Earth, right, is available now in hundreds of thousands of tons, right? And this is the first approach of the technology, and look the numbers that we are working with, right? But for reaching that material, we had to make some important decisions. As I say, we consider like ecology, we consider industrialization, we consider integration, right? So the first thing that we did was fibering. So that was one of the first decisions. Like we did fibering from silk for many reasons. Like first, fibering is scarce and is expensive, and its production and definitely its isolation is not that green, right? And that is a very important thing to remark, because there is a misconception that biological and green, or like ecological, right, are the same thing. And that is not true. There's a little bit greenwashing, right? For the extraction of fibrin, for example, we require to use lithium bromide, and that's an extremely aggressive pollutant. The same thing with cellulose, right? At some point, like in our history, cellophane, nitrocellulose, celluloid, right? All these biofilms derived from cellulose were very popular. Indeed, all the movies were recording celluloid, right? But these days, their use is residual when compared to other polymers, and specifically with synthetic polymers. Even if all these derivatives of cellulose, they are 100% biodegradable, right? And the reason of this is because cellulose is organized in the same hierarchical organization that I saw before, and dismantle that, like break down this hierarchical organization is quite easy until the microfibrillae level, where the paper is made, right? But going beyond that microfibrillae level, when you try to like separate like individual molecules, right, that you need for making those plastic, that requires like a hydrolysis using something at the level of like carbon disulfide or hydrochloric acid or sulfuric acid, like really strong solvents, right? And the problem of that is that we cannot avoid them. They are necessary for like going all the way to the molecule, right? So if we cannot avoid those solvents, or if we can avoid those solvents, right, what we will be producing is a cleaner technology. It's something that we can actually implement, but also a simpler technology that can be generalized to environments with a proper chemical waste management, right? Like, again, what we are not trying to do is to like solve a problem by creating like 5 more, right? So we are trying to learn from our experience with plastic and the problems of plastic and the problems of waste, right? And then try to make technologies that they consider all the lessons that we have learned so far. And the good thing is that we can avoid them. We can avoid those solvents, and we should avoid them, right? Because the biological model that we were following, the Omniset wall, used the cellulose at the microfibrillae level. And indeed, in the final form of our biomimetic material, the cellulose is in its microfibrillar form, right? So we avoid like going underneath. So we like on purpose decide this is how deep we are going. This is how where we are stopping, because from now on, if we move there, like our technology start to lose the ecological aspect of it, right, of the sustainability. So you can see in the image on the corner, there are like some objects of different colors. is also because we explore the sensitivity of the system to the purity of the raw material. So the brown objects are made of pure good, and the white ones are pure cellulose, and then there are like mixes of them, and there are like many different levels of purity for the cellulose, right? We try different technologies for manufacturing, variation of casting and molding, right? Like most of the balls and objects that are there are made by casting, right? We try additive manufacturing, we try subtractive manufacturing. And I'm going to focus a lot on additive manufacturing in this talk, what is remaining of this talk, and not because I think that this is better for an immediate and incremental change in packaging or in product production, right? Actually, casting and molding are much more suitable for mass production. But I'm going to focus on additive manufacturing because, as I will explain later, I believe that in the long run, additive manufacturing is going to play a much more important role on sustainability than techniques based on mass manufacturing, and they will allow us to decentralize production. But I'm going a little bit ahead of myself. So let me show you something that I think that even if this talk is going to focus on the end results, but I want to give you like a glimpse of how developing a technology and a material in parallel is a crazy task requiring insane levels of multidisciplinarity, right? I'm trying just to show you the results, but there are like a lot of work that I'm avoiding to mention because obviously I don't have time, right? So the results of that effort are actually extremely rewarding. So definitely it's a path worth covering, right? And the result of that is that we end up with a generally different manufacturing technique that with its own problems that nobody has reported before and some effects that we still struggle to understand these days, but also a technology free from the limitations imposed by a century of, engineering. Okay, let me try to go a little bit. So basically, we free ourselves from the limitations of the current technology. That was our problem when we tried to implement the acrylic and the chitin into existing technologies, right? That they are limited by the concepts of other materials, right? That they didn't fit the concepts of the materials that we were using. So one of the first things that it was very obvious is that working at room temperature without the constraints of a melting process and without the need to worry about solvents, because the printing is based on water, right? We can deposit as much material as we want in one go, right? So it's not like we have a limit of material that we can warm up and we need to distribute the temperature across a filament or anything like that, right? So we can literally like, put as much material as we can pump in. So that means that we can print fast, very fast and very big, right? And to highlight that versatility and the potential of the technology, we manufacture the Turbine Blade that you are seeing now on the screen, right? And that video of that Turbine Blade consolidates many aspects of the material in one go. For example, the grit at the core that you just saw has been optimized for both removing weight of a material from the blade, right? Like usual topology optimization, but also to improve the evaporation of the water in which the material is dispersed when it's being printed, right? Like the core of the blade is 3D printed, the outside is plaster, the aerodynamic finishing has been done, sanding it down, but everything is made of one single material, right? And think about that, right? With what other material can you do this? So in our first approach of manufacturing, following the principles of bioinspired engineering, we ended up with a technology that in many aspects, right, can look into the eye to plastic manufacturing in terms of price, versatility, scalability. But the good thing is that we can go much beyond, we can go like way beyond that, right? So a year ago, a couple of years, year and a half ago, right, we made the Hydra. So, and that was at that point, and still, I think still being the world's largest biological object ever printed, and the largest 3D printed object with any material in Southeast Asia, right? And I can make a stronger statement because we left behind the competition with plastic printing, and we are competing with concrete printing, right? And let's be realistic. I mean, like, that's concrete printing is in the range of houses, right? So, but if you remove that, if you remove concrete printing, there is like, we are one of the largest objects ever produced, right? And that's important to remark, that we are discussing, and it's important to remark because what it highlights, right, is that we are not discussing a potential technology that needs somehow to increment its production to cope with a possible demand at the level of plastic, or needs to be scaled up to manufacture an industrially relevant scale, or that needs to find a way to lower its cost. That is where we were like 10 years ago with Israel, right? Like, we are talking about a technology right now that we are exploring for inclusion in industries that they go from automobile to furniture, right, to construction to high power electronics, right? And if you realize, until now, I have barely mentioned the sustainability of the technology, right? I haven't like used that card yet, in a sense, because the thing is, like, it is embedding the principles of the technology. Because not modifying the biochemical molecules to facilitate the fabrication, and focusing on the bioinspired aggregation based on water and simple chemistry, that tower there has the same integration in the ecology of Earth as a mushroom. And there is no trick here. There is no kind of like PLA-like of a statement saying like, it's biodegradable, but you need to recover it, and as you will do with any other plastic, and you need to put it into a biodegradation plan, right? So, because as I say at the beginning of this talk, I believe that for to be successful, we need to be competitive in terms of technology and economics, and not base our succeed on the ecological awareness of companies and population, right? So for the technology to be adopted, it needs to represent an industrial advantage on its own, right? And the sustainability needs to be the result of the paradigm created by the technology. It won't never work if, like, I ask you, like, okay, it will be more expensive. You won't be able to do what you are doing these days, right? But it's for ecology. We know now that that doesn't work, and it's not working, and the problem is getting worse, right? So, but the thing is, like, at the end of the day, we are developing a technology that is in the current economy, right? So we haven't changed the economy yet, right? Even if that is our goal, and that means that we can and we should make decisions based on the current industrial tools for addressing sustainability, right? So we cannot ignore the current paradigm for our technology. So what we did was a series of life cycle assessments of the technology, right? Like, we try to understand what will be the main factor contributing to the impact of the technique if we implement it in the current production processes. There is something that we are overseeing, right? There is something that we are not seeing. That if we actually like upscale this and we put it at industrial scales, and we even like assume that can like cope with the demand for the whole world, right? What will be like the weak points? Are we making another or creating another issue, right? For those of you who are not familiar with these studies with an life cycle assessment, with an LCA, right? Basically, an LCA, what it does is translates into quantity. Can be energy, can be carbon dioxide, the different aspects of an industrial process, and then take those values and aggregate them to as a way to compare like different alternatives of the process. It's a tool that it works by comparing different systems. As I mentioned before, chitin and cellulose can be sourced from many places, but depending on the sourcing, you need some extraction process or other, right? Or you need to bring them from longer distances, depending on where you are going to use them, right? So all those factors are the ones that you can include in the LCA, all those variations, to see how they affect the impact or the environmental impact of the technology. So we focus our study on the sourcing of the raw materials, that is key, right? And in the case of cellulose, it can be directly extracted from green plants or from recycled sources, right? It can be pull out from the waste. And in the case of chitosan, can be extracted from the bioproduct of the fishing industry, or from fungi, or can be extracted from insects, right? There are like many options to get chitin, right? The conclusion of those studies was always the same. transportation is by far the highest contribution to our process. And if you are familiar with similar studies for any material at the end, right, this is not a surprise. We know that 1/5 of the global carbon emission come from the supply chain of 20 multinational companies, right? 1/5 of the pollution just from moving things up and down around the world. So that is the impact of transportation in our environmental issues, right? Chitin extraction and the source is the second contributor to the environmental impact of our new technology. And surprisingly, the source of cellulose doesn't matter much because the production of paper pulp has been very well fine-tuned for centuries, actually, and these days is really really well adjusted process. But the thing is, like, all of these, right, is only true if you assume that choosing one source of other is not going to affect transportation, right? Like, we know that the process to obtain cellulose is equally clean if it's like a raw source or if it's a recycled source, but like the point is that that's not true. I mean, like cellulose, virgin cellulose and recycled cellulose, they live in different places in the world, right? So we basically what we did with the LCA, right? So was to characterize, so to recognize what are the areas that we can improve. And transportation is an issue. It's a general one. Every material has it. But the good thing is, like, we are not any material. We are the most ubiquitous organic polymer on Earth, right? And that means that we are being produced in thousands of tons in every ecosystem, in every corner of the world. It means they are everywhere. So transport a material from a place where you have that same material doesn't sound a great move. It's something that we do for plastic and we do for like more localized production of materials, right? But in the case of natural materials, that is like something that we really don't need, right? So what we did then is, like, if we don't need that, right? Because these moving materials around is a need that we borrow from the current processes, but we don't have, right? So let's try to kind of use that in our advantage, right? So let's first analyze carefully the technology as we have been describing it so far, right? So we have a free-form technology based on additive manufacturing that can produce almost any geometry, right? And that technology is linked or is based on materials that are anywhere, right? So we are talking about producing anything anywhere. So we are not talking about like a circular economy. We are talking about like circular regional economy, where materials are potentially produced, manufactured, and degrade in close regional areas on demand with minimal transportation. And that's the advantage of using the most ubiquitous organic polymers on Earth. And this might sound as a fairy tale at this point, right? But it's not even a hypothesis anymore. It's not. It's a hypothesis. Was a hypothesis like a year ago. It's not anymore. So when I start this talk, I say that one of the problems of waste is the urbanization of the population, right? Like, people live in cities, produce an average of 5 times more waste than people living in rural areas. And that's a problem for us, because a technology based on biomaterials, by definition, will struggle in an urban environment as compared to, for example, a region where you have agriculture or you have forest, right? Where you have like abundant and homogeneous production of materials, right? You produce the same material in very large amounts in a very good quality, right? So a city has waste. That's the only thing that they have. And this is like the only thing that cities produce in a very efficient way, like waste. And that's the problem that we are trying to solve. But the good thing is, like, it's also the solution to our problem. Because in the urban waste, there is a lot of biomaterials. The waste profile of a regular city, in the case, in the specific case of the slide, Singapore, right, looks like that in the corner, right? There are 3 main streams. that are the target of waste reduction. There is plastic, there is food, and there is paper and cardboard, right? So finding cellulose in an urban environment, in the waste of an urban environment, is easy. You have like the paper and you have the cardboard, right? The source of chitin is a little bit more difficult because it's hidden in the waste, right? Because chitin is an abundant polymer, but it doesn't have a clear industrial application, and therefore it's not a common byproduct of urban life, right? But the good thing is, like, we are not playing with the old rules. We are working with nature, and all its ecological cycles are supporting us in a sense, right? And nothing can beat nature. Like, literally there are like millions of options to take the very heterogeneous like waste on a city and transform it into a homogeneous composition containing chitin, right? That's the good thing of like be working with nature. You can use those ecological cycles, and you can use all that metabolism for your advantage, right? So in order to do that, in order to take like a biomolecule and transform it into the molecule that you want, you need like what is called a bioconverter. And there's a very few bioconverters as efficient as the black soldier fly. So there are many reasons why I choose the black soldier fly as a bioconverter in my experiments, right? And to transform waste into chitin instead of just a microorganism as a fungi or other chitin producing animals, right? So the main things or the main aspects, right, are listed there on the slide, right? Like black soldier flies can be utilized, they can be used in urban environments. It's a species that is endemic in most of the world, so there is no issue if they escape or they don't become or they don't disturb the ecology of the place, as they are actually like there in the wild, right? They process everything efficiently, from animal manure to food waste, right? It has a conversion rate of like 1.5 kilograms to 1 kilogram, something around those numbers, right? So those numbers are actually like completely insane. If you think like a cow, it needs to like take like 10 kilograms of material in order to produce 1 kilogram of cow, right? What we are saying is that these insects, they take like 1.5 kilograms and they transform it into one. So look like this enormous difference on the bioconversion, right? The black soldier fly, or the larvae of the black soldier fly, is 43% protein. And that's basically what it gives value to the process, because the protein is what it can be used for food and things like that, right? And that's important because it means also the chitin is a byproduct of the bioconversion, right? It's not the purpose. So, and on top of that, there is a very practical issue that makes black soldier fly so popular around the world, right? So is that when the animal is done feeding, spontaneously abandon the feeding site looking for a dry area. So you can, so you don't need to separate the material that you are bioconverting, your waste, from the animal that is doing the bioconversion, because the animal does it on its own, right? And I can continue like forever giving you reasons, but I'm actually like 50 minutes over the 50 minutes right now. So so I will try to sum up like all these reasons in one file, right? Like the idea that the bioconversion of organic waste by black soldier fly, by BSF, right, has an annual implementation growth of like 33%, right? Like it's growing on a 33% rate all around the world, right? In countries with degrees of development across all the spectrum, from Malawi to Switzerland, everybody's using this animal for bioconversion. And that is important because sustainability doesn't understand about borders or economic status. We either all become or become sustainable and do that transformation together and help each other, or nobody go there. Right, so sustainability doesn't understand of borders. That's a man-made, or nature doesn't understand of borders. That's a man-made kind of concept, right? And actually, like I'm going to show you this video because I think give you like an amazing idea in a very graphical way what is the efficiency, or the bioconversion efficiency of black soldier fly, right? That video covers basically less than 4 hours. So if you go to the website at the end of the video, there's a bunch of other videos where they throw all sorts of stuff, like fees and things like that. I totally encourage you to check them out. I find them kind of like gross and mesmerizing at the same time. But also, if this is the first time that you see that and you are used to the usual composting rates, right? The fact that this is only 4 hours is completely insane, right? So let's go back to the urban manufacture. I think that now is clear why we choose the black soldier fly. Because we are starting to go to this point to where we can glimpse the potential of developing a technology as a part of ecological cycle. That instead of like fighting nature, we can tap on the bioecal solutions to solve our problems. Think what you just saw with the hamburger and how absolutely careless those larvae are about the composition of the waste of the diet, right? So now think about all the problems that we were describing at the beginning about like the plastic recovery based on like the need to sort out materials by composition and by colors, right? So these larvae, they do it like on their own. They really don't care. They sort them things and they transform all these kind of heterogeneous mix of components into one single thing, an insect, right? So we can use them to complete the loop. So we took the paper waste, we ground it, we fed the insect, we start the chitins, right? And we demonstrate that we can produce the material in Singapore. That is, I don't know if you are familiar with Singapore, but it's a fully urban country without like, and we did it without importing any material from outside, only using waste. And for a country without natural resources and fully depending on foreign countries to be supplied, as is Singapore, right? The implications of that are not only ecological or economical, they are also a matter of national security. And we have seen, like with all the coronavirus, we have seen like how this kind of like keep your production regional or local is so important when like the supply chains, they break, right? And we have seen how easy it is to break the supply chains in a crisis, right? So, but the real relevance of the objects there is that the cellulose and chitin are produced by many organisms in every ecosystem. And we choose our sources based on the available resources, right? And that ability to choose is the important takeaway, because now we can link general manufacturing to the surrounding ecosystem. And we can do that even in the most common but complex circumstances as is an urban environment, right? And that's the key here, right? Like this idea that you can correlate your environment with your manufacturing. And in our case, we choose black soldier flies and we use like paper waste, but that doesn't mean that's the only solution. Cellulose is produced by many places in many organisms, right? And same thing for chitin. So your solution might be different, but it will be adapted to the environment where you are implementing it, right? But let me just go a little bit 1 second to the robotic part of the technology, because as they say, like the devil is in the details, right? I have been talking a lot about general manufacturing, and I want to highlight that what I mean by general, right? So because we only use one extraction system and one robot in our experiments, the ABB that is in the picture, right? Is the same one that you have been seeing for the whole presentation. The only physical change we make is the tip of the nozzle. And that enables us to fabricate from the 0.5 millimeter precision of the Hydra, mini Hydra that I just saw you printing, right, to the 5 meters very big Hydra that is on the picture, right? Think about that. Just let it sink. From 0.5 millimeter to 5 meters with one manufacturing technology and one material, right? That's actually like very few technologies can actually claim that. So let's remember, let's start wrapping up because it's over the hour now. So let's start remember the beginning of this talk, right? We say that materials define economies, and we as material scientists tend to say this in a very careless way. That's like almost like any talk about material science that you have you have heard probably start with like, oh, the age of the history are defined by materials, right? Without even like fully understanding what that means. But the thing is that that is actually true and a very strong statement, because it's not the other way around. And in my opinion, that is what we are doing wrong. We are trying to keep our economy, but change the materials that define it, right? We are trying to keep our economy, but get rid of plastic, right? Without realizing that our economy is a consequence of plastic, right? So in this case, biomaterials are everywhere and they're in continuous renewal, right? Therefore, the natural economy is regional and circular, right? Because that is indeed the way that they were conceived to be used and to work, right? And being sustainable is just the type of the iceberg, right? It's not the purpose, it's a side effect, right? Can we regionalize the whole production? I mean, like we can regionalize like a lot, but not all of it, right? And of course we cannot. So you always need to transport some functional materials and specialized components, but we can make the production of many items, right? Like packaging, for example, that they started this talk talking about, right? Is one of them. We can do them like much more efficient and much more sustainable by regionalizing them. But that's not the only change. Sustainable manufacturing has been presented historically, right, as a need, because the mess that we are doing in our planet, and it's not presented as an opportunity, right? But linking manufacturing with the surrounding ecosystem, that is basically like the basis of our work and the kind of like the research that we lead, right, is this linking of manufacturing and ecosystems, right? And that allows us to produce in a very efficient way and do things that we have, that they have been completely out of our technological reach until now, right? And to demonstrate this, to actually highlight, like we are not aiming to substitute plastic, we are aiming to like bring like new materials and new technology that they can do things that plastic cannot do, right? We target a extreme problem that is currently not, can be solved with the system manufacturing technology. That is the general manufacturing in the most extreme place to fabricate something. And that is a dead rock in the middle of the universe. Because going to Mars, right, has been like the realm of science fiction for a very long time. But now the most conservative estimations calculate that we'll be on Mars before like 2040, right? That means that we, like everybody in this talk, right, is going to see it. It's our generation. Our generation will see a human going to Mars. And we don't know who will do it first or exactly how we'll do it, but we know for sure two things. First, that the problem is very different to stepping on the moon. We cannot go to Mars, step there, and come back. Going to Mars requires to stay there. And while bringing a human all the way to Mars is a great challenge, right? The challenges associated to stay there are completely new to us, right? Like establishing humans is necessary, but at the same time, it's a new challenge, right? Second thing, we don't know what else the humans they are going to bring with them, right? But if there are humans, there is going to be biology. That's for sure. Because for humans to survive, we need a supporting ecological system, producing nutrients, producing oxygens, right? And with the scarcity of resources on Mars, that process needs to be as efficient as possible. And efficiency means no waste. It means circular manufacturing. So surprisingly, or not, right, the technological needs to reach Mars are the same ones that we have been discussing for the last hour, right? It's exactly the same thing. So we design the set of flows and processes that are on the slides, right? Like we decide, okay, can we actually like solve this problem? Can we use our approach of linking manufacturing or bioinspired manufacturing with ecological cycles and with biochemical metabolism, right? So we made it based on the current prototypes and technologies that are being explored for NASA and ACA, right? We contacted people from the Lawrence Berkeley National Laboratory and from the NASA Ames Research Center. surprisingly responsive and friendly people, by the way. And we found the routes to produce the chemicals that we will need as a byproduct of fermentation or electrolytic hydrolysis, right? So, so the only thing that we will need is to sip a couple of electrodes to produce all the chemicals that we need for manufacturing with biomaterials, right? And we found a lab in the university in Central Florida that is producing regolith simulants, right? It's producing a mimic of the soil of Mars, right? That is, and that is a key ingredient, right? Because our materials have been produced based on the ecology of Earth and assuming a bountiful biology, right? With large amounts of cellulose, large amounts of chitins, right? Like, but that's obviously not the case on Mars, right? In Mars, there is only one thing, soil, right? But on the other hand, as I said before, nature is really good finding solutions in adverse conditions. And that's the whole point of life. It's actually like open its way through adversity, right? And indeed, the integration of an inorganic phase has been one of the focus of our research because they use that biology make of it, right? It's a common strategy in nature to not only explore different mechanical properties, but also as a method to grow beyond the size or limits of an animal by incorporating components that they have like zero metabolic cost, right? If you take like a stone from the environment and you incorporate, or a mineral from the environment and you incorporate in your system, right? That is like something that you don't need to metabolize. You don't need to produce as you need to produce chitin, or you don't need to produce cellulose, right? So it's just basically coming out for free, right? And specifically in Nacre, that incorporation is made in chitinous organic matrix. So it's basically a mineral and chitin, right? And we know a bit about how to make in Nacre, and we know a lot about how to manufacture with chitin. So, and we know now that we can do like that manufacturing using only waste. So we developed a material that is organic and organic composite that we call Bioreef. We optimize it based on three aspects, right? It's ability to be manufactured, its mechanical properties, and the metabolic cost of its production, right? So we keep in mind that we are coming to the extreme case of energy and material sources, right? So metabolic cost is extremely important thing to keep in mind, much important than mechanical properties, if you think about it. And we produce that material on the slides, right? And if you see like where it looks, what is the material, right? So you see that actually it doesn't look like amazing, right? With mindset of healthy kind of like mindset, right? The mechanical properties might not look amazing, but considering the low pressures and the gravity of Mars, they actually are. But not only that, it's a great material because it can be done. Because you can have like materials that are much better mechanically, but they cannot be done because the requirements in terms of energy, in terms of resources, right? Because in an hypothetical Martian ecosystem, as it should be on Earth, as we are like kind of like realizing now, right? The mechanical properties are at the same level, if not below, than the ecological integration and the metabolic cost of the material. And that's what we are actually realizing now, like paying attention on Earth, right? Like the idea that actually like maybe we have been focused a lot on material and mechanical properties, right? Without like considering what is the efficiency of those materials, and that of course involves ecology, right? So we demonstrate that we can produce like complex shapes with extremely good definition, and we use a myriad of techniques with this Bioreef, right? But the important aspect of the technique are that it's based on one single material, right? It's focused on versatility, so that is something that is very important. You cannot like produce like tons of chemistries and tons of different processes on Mars. You need to keep it simple. So if you can use the same material for making tools and for making buildings, perfect. One single material, right? It's focused on integration in an ecological cycle, on a potential ecological cycle with humans, where you need to produce oxygen, you need to produce food, right? and it can be produced in large amounts in really low energetic cost, right? And if you think about it, all these needs, right, are exactly what we have been talking like during this talk for the product production or packaging, or like all the samples that we have been giving, right? So all these needs to like amounts and economy and integration, right? And that's the beauty, and that's the takeaway from this last part, and why I put like all these slides about Mars at the end, right? Because we are not talking about a replacement technology. The technologies that could enable a sustainable development on Earth are also the technologies that are necessary part and of the what probably is the most symbolic achievement of this century, or will be the most symbolic achievement of this century, right? That is the transformation of the human race into an interplanetary species. So we are not talking again about kind of like replace plastic in a choppy way and try to like go back to like old technologies. What we are talking is completely the opposite. We are talking about like bringing like making the technology that will allow us to do one step further, right? And I'm going to wrap up now. I mean, this has been like a real long. I mean, much longer than what I expected. I'm really like over 1 hour right now. So I started this talk with showing you like a fossil record of an insect, right? And I end up in Mars. And I haven't focused on the immediate applications of the technology in a specific product, because I wanted you to like understand the transformative aspect of sustainable manufacturing and the possibility to link ecological cycles and manufacturing. What are the possibilities of that, right? What are the implications of that they go way beyond like an incremental improvement of a certain application. I mean, like take like for example the case of packaging that triggered the beginning of this talk, right? Like we can integrate this production with the surrounding ecosystem and start like walking the path towards regionalized production. For example, in a first approach, for example, we can delocalize the sources of the materials for packaging, right? As we already did, and bring the materials to fabricate packaging closer to the packaging itself, right? The product and the packaging, they can be produced as part of the same system, right? So the conclusion here is that we have been treating the problem of waste, assuming that somehow that we have reached the peak of human development with the invention of plastic manufacturing, and that any solution needs to be integrated in the paradigm imposed by plastic manufacturing. But I believe that we are in the verge of a huge transformation. Like not only here, we are seeing how biology is leaking and integrating in every other engineering field, from food production to material synthesis, right? And they give us the opportunity to develop technologies fueled by these incredible powerful tools and process of biological systems, as we did for our materials. And those technologies enable us to achieve goals that are unreachable with our current technology. And one of them, but not only one of them, right, is to achieve a sustainable development. And this is why we call our work, or like what we are aiming, the biomaterial age. Actually, there is an article published last year, right, that summarizes a little bit like all these visions. So I really strongly encourage you to find like more if you are interested, right? So I think I'm going to wrap it here. So thank you very much for listening, and I hope that you you enjoyed the talk, even if it was like way too long. So goodbye.